Welcome to lecture series. We have seen if we consider a linear operator on a finite dimensional inner product space, then if there exists a order basis B for the corresponding space V and the matrix representation of T is some upper triangular matrix. If the T is normal, then the upper triangular matrix is basically a diagonal matrix. Now, question is how to give guarantee that there exists an orthonormal basis for the space of finite dimensional complex inner product space for which operator will have a matrix representation as an upper triangular matrix. Today we are going to answer that question first. If I answer that question, then I can immediately say that if the operator is normal matrix, then that upper triangular will be diagonal matrix. Consequently, we can say the linear operator, the normal operator is diagonalizable over that space. I mean to say the space will have a basis consisting of eigenvector of the given operator T. So, let us quickly prove that results, that is what is the condition under which we can say that space V will have a orthonormal basis such that the operator defined on that space will have an upper triangular matrix representations. So, it is like this, let V be a finite dimensional complex inner product space, T be a linear operator on it, then there exists an orthonormal order basis for V such that the matrix representation of T with respect to the basis is an upper triangular matrix. So, the proof what we will do it here by induction on the order of the dimension of the space. So, we shall prove this result by induction on the dimension of the space V. Let dimension of V equal to n. Assume the result is true for a finite dimensional complex inner product space of dimension less than equal to n minus 1. So, consider the adjoint operator T star of T. So, definitely there exists a non-zero vector, I will say non-zero unit vector without loss of generality, unit vector alpha belongs to V such that T star alpha equal to C alpha for some C belongs to the field of scalar on which V is defined. Okay. Consider W as a subspace, which is orthogonal complement displacement of the subspace spanned by alpha. So, this implies, note that the subspace spanned by alpha is T invariant, I mean T star invariant, T star invariant. So, this implies W will be T invariant according to our previous results. Consider S as a restriction of T on W. So, this implies S is a linear operator on W of dimension n minus 1, because dimension of that subspace spanned by only singleton element alpha is 1 and dimension of the space V is equal to n. So, dimension of the orthogonal complement that subspace will be n minus 1, that is dimension of the W will be n minus 1. So, according to our hypothesis, there exists an orthonormal order basis for W such that the matrix representation of capital S with respect to it is an upper triangular matrix. Now, consider B prime which is equal to B and alpha equal to, let us consider alpha 1, alpha 2, alpha n minus 1 and alpha, where B equal to alpha 1, alpha 2, alpha n minus 1. So, then we have matrix representation of T with respect to this order basis equal to, certainly will have a upper triangular matrix like this, because if you see the definition of the matrix representations, T of alpha which is equal to C into alpha, that will be the last row. So, it will be the last row. So, and the first n minus 1 rows is coming as a consequence from the matrix representation of your capital S, since capital S is the restriction of T on W. So, therefore, I will have the matrix representation of T with respect to this new order basis B prime will be like this. So, this gives the proof that there exists an orthonormal basis under which the operator T will have an upper triangular matrix. Okay. So, now let me conclude. So, this implies, I can say, if T is a normal operator, operator on a finite dimensional complex inner product space, then there exists an orthonormal order basis say B star such that matrix representation of T with respect to B star equal to a diagonal matrix, because if the matrix representation of a normal operator with respect to some order basis is upper triangular, then that certainly that upper triangular is a diagonal matrix. Therefore, I can say that the normal operator T will have a basically diagonal matrix representation. So, this implies if B star equal to alpha 1, alpha 2, alpha n, then T of alpha 1 equal to something like I can say C1 alpha 1, T of alpha 2 equal to C2 alpha 2 and T of alpha n equal to Cn alpha n. This implies alpha 1, alpha 2, alpha n the basis of course orthonormal basis consisting of eigenvectors of T. So, now let me come to some small corollary type. Okay. So, I can also come to the conclusions of the my last theorems, that existence of order basis under which the operator can be written as an upper triangular matrix. Comes the consequence of these results that for every complex n cross n matrix A, there is a unitary matrix capital U such that U inverse AU is an upper triangular matrix. So, the proof is exactly same what I did in the case of self adjoint operator case. What I will do? I will quickly give the proof for this proof. It is like this. So, given A as an n cross n matrix, n cross n complex matrix. Okay. So, consider the space of column matrix over complex plane C of dimension n, that is C n cross 1, along with standard inner product on it. Define a linear operator T on C n cross 1 as T of capital X equal to A time X. I mean to say the matrix representation of the operator T with respect to standard order basis in C is basically capital A. So, by previous results there exists an orthonormal basis, say B equal to alpha 1, alpha 2, alpha n for the space V equal to C n cross 1, such that the matrix representation of T with respect to that order basis T equal to an upper triangular something like this. So, let me consider that is capital S is upper triangular matrix like this thing. Then consider U which columns are alpha 1, alpha 2, alpha n. So, U is a unitary matrix, We have here T of alpha 1 equal to A of alpha 1, which is equal to what? This will be first column of capital S, I will say that S 1 1 alpha 1, because it is upper triangular matrix. So, T of alpha 2 will be equal to what? T of alpha 2 it will be like this 2. So, A of alpha 2 this will be equal to S 1 2 alpha 1 plus S 2 2 alpha 2 according to the definition of the matrix representations. I will certainly will have like these things. So, in this way we will see that your A of alpha n will be equal to sigma S I n I equal to 1 to n alpha I. So, this implies I am getting A into alpha 1 to alpha n equal to alpha 1 to alpha n into that upper triangular matrix like this. So, this implies A u equal to u into capital S. This implies your u inverse A u equal to capital S. So, that is the proof. So, we see that one can also have unitary matrix such that u inverse A u equal to an upper triangular matrix. This is also important results. So, now we have seen that a normal operator defined over finite dimensional complex inner product space is diagonalizable. I mean the space V on which the normal operator is defined has an order basis which is orthonormal and consists of eigenvectors of the normal operator T. Okay. So, based on these results, let us write down one nice theorems which is basically conclusion of the whatever we have done. So, let me summarize what we have done so far regarding the normal operator. So, we have seen the normal operator defined over a finite dimensional inner product space, of course, that has to be complex, then corresponding space will have order basis which is orthonormal and the consists of eigenvector of the operator T. So, based on these results, let me talk about one nice theorem is called spectral theorems. It is like this, it is saying that let T be a normal operator on a finite dimensional complex inner product space V, or T a self adjoint operator on a finite dimensional real inner product space, and C1, C2, Ck be the distinct eigenvalues of T. Let Wj be the characteristic space associated to eigenvalue Cj, and Ej the orthogonal projection of the space V onto Wj. Then Wj is orthogonal to Wi for j not equal to I, and V is the direct sum of W1 to Wk, and the operator T equal to C1 into E1 plus C2 into E2 plus Ck into Ek, which is called the spectral resolution of the operator T on the space V. Okay, so, let me give the proof of these results. Already we have done similar type of problems long back in this course. So, it is basically repetitions. So, quickly we will recall what we have done, and it will also easy to understand these nice results. So, we have to show that if I not equal to j, Wi is orthogonal to Wj. Let alpha belongs to Wi and beta belongs to Wj. Let T of alpha equal to say C I alpha and T of beta equal to C j beta. So, this implies inner product of C I and alpha beta, if I consider like this is equal to C I alpha and beta, which is equal to T of alpha and beta. So, this is also equal to inner product of alpha and T star beta. This implies C I inner product of alpha and beta, which is equal to your inner product of alpha, and T star beta will be equal to your D bar beta, which is equal to D times inner product of alpha beta, not D, it will be Cj. So, Cj bar beta as will be Cj this one. Okay. So, this implies for Ci not equal to Cj, we have Ci minus Cj into inner product of alpha beta equal to 0, implies inner product of alpha beta equal to 0. So, this implies Wi is orthogonal to Wj. Apart from this, we will also have since T is diagonalizable, so we already know that implies V will be direct sum of W1 plus W2 plus Wk. V will be equal to sum of subspaces W1 to Wk, and for any alpha belongs to V, we will have alpha equal to alpha 1 plus alpha 2 plus alpha k, where alpha I belongs to Wi, I equal to 1 to k, and Wi is range of Ei. So, this implies alpha can be written as, so alpha 1 will belong to W1. So, I can write down alpha is equal to as E1 alpha plus E2 alpha plus EK alpha, because EI alpha equal to alpha I. So, based on that principles I can say alpha equal like this. So, this implies the identity operator equal to E1 plus E2 plus EK, and here this projection operator EI, so they satisfied EI into EJ equal to 0 operator when I not equal to j and EI square equal to EI. So, we have I equal to E1 plus E2 plus EK, and alpha is equal to alpha 1 plus alpha 2 plus alpha k, already you written. So, if I multiply T to the this equation star to T into I will be equal to T E1 plus T E2 plus T EK. So, this implies, see, T of alpha equal to T E1 of alpha plus T E2 of alpha plus T EK of alpha. So, this implies this is equal to T E1 alpha plus T E2 alpha plus T EK alpha. So, this is equal to C1 E1 of alpha plus C2 E2 of alpha plus CK EK of alpha, because EI alpha is belongs to Wi. So, when T operating on that, it will be Ci into EI alpha. This implies the operator T equal to, I can write down C1 E1 plus C2 E2 plus CK EK, which is called as spectral resolution of T. Okay. And here this is called the spectral resolution of the I, spectral resolution of identity operator. See, interestingly, we can immediately check that all the projection operator is basically polynomial. How? See, it is like this. Note that we have T equal to C1 E1 plus CK EK. So, this implies your T square will be equal to what? It will be, you can immediately check, it will be C1 square E1 plus CK square EK. In fact, T to the power R will be equal to sigma Ci power R and EI I equal to 1 to k. So, this implies for any polynomial over the corresponding field on which the space is defined, we have f of t will be equal to sigma f of Ci and Ei I equal to 1 to k. In particular, when f of x equal to Lagrange interpolation polynomial, say Ejx, which is equal to x minus Ci by Cj minus Ci. over the I not equal to j, that case. So, in this case we will have what, see this polynomial having nature such that Ej at Cj equal to 1, Ej at any other value of Ci I equal to 1 to k will have equal to 0. So, for choosing this type of typical polynomials, I will have Ej of t will be equal to sigma of Ej Ci and Ai I equal to 1 to k, and this is equal to canonical delta Ij and Ei. So, this implies Ejt will be exactly equal to Ej. So, because I equal to j, then only I will have is equal to 1, otherwise 0. So, the projection operator is basically a polynomial in nature. So, this wonderful results will be used in different places of our analysis. In the case of any numerical calculations, numerical solution of the PD, one has to use this concept of normal operators, and this normal operator defined over the finite space, which gives a set of orthonormal bases which is consist of eigenvectors. This helps lot to even finding solutions, even it will utilize in singular value decompositions, which I am going to do it in coming classes. So, you will see the beauty of this normal operator in our next class also.